today we will begin the class for H2 physics. All of you are J1s, right? Is there any secretive J2s inside? No, okay, but anyway, if you are here, it's fine. Okay, anyways, so today we'll be looking at the revision for waves and superposition. Specifically, I think because this topic is new for most of you guys in your current J1 syllabus, if you got your school has already started, and it's one of the more confusing topic because why? It's something that you have not seen before. Number two, it's not as easy as kinematics and dynamics. Not that kinematics and dynamics are easy, but it's just slightly harder. Okay, so reintroduction. Basically, for those who don't know OVERMUGGED basically makes up of a lot of young tutors like me. The Chem one still don't know how old I am, so the physics one will not know how old I am, but we are all very young. We are at least a university graduate. I'm a master's graduate myself, so that's how old I am. And either we graduated, or some of us are currently teaching in schools. So like the teacher next door, he's teaching in RJ right now. If you are anyone from RJ, he's teaching English, Dixon, right? Anyone of you are at RJ? Yeah. Huh? Oh, he teaches job. Oops, then why is he teaching English? But anyways, I am not in the humans world, so I don't understand how it works. But so in this case here, we are not so boring tutor. So if you have any, like life issues, boyfriend, girlfriend, relationship issues, I dated my husband for 11 years. I think we are 11 years together, so I can provide some sort of advice. But then again, he's my first boyfriend, so I can't really provide much advices. If you have any parental issues, can also talk to us if you need to. Understand? Okay. Just don't stress. Mental health is important. Survive. Studies is not everything. Yeah. My mom always teaches me, if you can't study, never mind. As long as you get a skill, you can survive. So if you don't study well, learn a skill. That's all. Okay? But don't learn like skills that don't make money. Okay. Now, we have many different branches in Singapore so far. Our flagship branches are Bukit Timah. Parkway Center is the newly renovated one. So if you guys stay nearby there, you can go there. What's cool about Parkway and Parkway Center especially is because we have a study lounge there. So we try to incorporate like a study room so you all don't have to go to those cafe and buy those really expensive $7, $8 latte. Down there got free Milo, free snacks, free whatever. Got plugs also, you can go there and study. Understand? It's at Parkway. We also have Serangoon. So these are our 3 flagships. The other places, Toa Payoh, Jurong East, Woodlands, are currently like, we rent spaces from people. So it's not as fancy as our current flagship ones, which is truly ours, where you can just walk in like a boss, key in the password, and then just sit inside there. Okay, so these are the spaces that we have, and we have an upcoming new space in Tampines in 2024. So if you want, you can go to Tampines, and I like it there because I stay there. Okay, anyways, self-introduction about myself. So same thing, I will not say my age, but I've been teaching for 12 years, and I have been I graduated from aerospace engineering. So for any of you guys interested in going to aerospace, you can ask me. It's a course that for girls a lot of guys, a lot of guys. That's one. Number two, it's also a course that is very heavily dependent on math and science. Okay, so when I went there, basically I was like not to say competing, but I give up competing because my classmates were all Air Force pilots. So just imagine the competition that I had. They flew a plane before and I didn't fly a plane before. So they understood what the professor was saying. I totally did not understand what the professor was saying. So that's the competition that you can face in aerospace. Then for my master's, I did in education. So both I did the art side and the science side, and it's completely different studies. So if you have any question relating to those 2 spectrum, you can come and ask me as well. Understand? Okay. Now, the next thing, wait, I just realized. For those online, can you all see the screen? Anybody can just give me an indication if you guys can see the screen. Can okay. Yeah, okay. Good. I can't see the screen on my side. Okay, but anyways, so a self-introduction by myself, I already said that. Next thing, three things that I like. Number one would be, oh, you give me a while. Okay, never mind. I think I know why. Okay, I think there's a glitch in there is like 5 participants here, but there's 10 participants here. So I don't know why I'm on 2 Zoom accounts. But anyway, for those in this current Zoom account that I just sent in the chat, ignore the one that, can y'all just join in the link, those who receive a link in the chat, just join this link inside. Okay, thank you. Okay, so anyway, as I was saying, a little self-introduction about myself as well. If you want to know more about me, you can ask me privately. Not that I will share a lot about myself as well, but it's just that if you want to know, I'm a massive Taylor Swift. The 2 guys behind is like having some picnic on their own like that. Yeah, but anyways, enjoy the picnic. I'm a massive Taylor Swift fan, so if any of you guys going for the concert, yeah, you'll probably see me there for 2 days. I'll be going for 2 days. Yeah, but yeah, I know, right? But I got extra tickets, so if maybe y'all do well, I can give you one. If y'all do well and y'all join my class. If lah, okay? Because my brother and his girlfriend got pregnant, so they can't go. Can't possibly jump with the big baby, right? So the big belly, so they're giving out their tickets. But anyway, I'm also a Formula One fan, so any of y'all going for Formula One next week, yeah, y'all will see me there possibly. Okay, and then I love food and traveling. So if you guys try to find me in December, I probably won't be in Singapore because I'll probably be traveling somewhere else. So I've been to places like, for example, South Africa, where I met that guy and he taught me the entire lyrics of what's the Lion King song, Circle of Life, because it was in Zulu, I think that's what he told me, or Zola, there's some African language. Then he literally translated every single sentence to me in African. Yeah, so it was quite cool. He's a tracker, so basically means he specifically studies animals' behavior and look at the ground sand movement and whatnot. Then he can look at it and be like, oh, there's a lion lying there or something like that, stuff like that. So I don't know whether he's lying to me as well, but anyways, I believed him. Then that's me in Vietnam and that's me in Switzerland. So anyways, I love to travel. So if you guys want to go travel next time as well, you can find me. My retirement plan is to set up a travel agency and then after that, travel with people that I like and then go tour around the world, spending other people's money. Okay, anyways, what are we doing today? Basically, we're going through some of the key concepts as well as the misconceptions that you guys have, especially for superposition. I think wave shouldn't be a problem because most of you guys come from pure science background. Anyone from combined science? No, everyone from pure science background. So you have probably, even for combined science, you have probably also done waves in combined science. So What we'll be focusing on mainly would be for superposition today as well. But I would like to highlight some of the things that you need to take note in waves. Then we'll look at some examples and some commonly tested questions. Okay? So I've given you guys two things. Number one, other than the revision kit that you guys have, first things first, you have the summary. Those online will also receive a concept map. So for every topic, I usually do a concept map for my class so that at least, right, all the information that you need is on this one or at most two sheets of paper. And by what I mean by everything will be tested, right, is literally everything will be tested on this paper. Every single concept, every single word, every single asterisk that I put. Understand? Obviously, if it's not exhaustive enough for you, go back to your notes and keep adding on to this concept map. The idea is when you're traveling to school during that 1-2 hour travel journey, you don't want to be looking at all your notes and don't know where to start from. So you start from this sheet of paper at least. Okay. Second, I also given you guys some questions that we'll be doing today. The question is a little bit blurry, so look at the screen if you can't see. So apologize because the printer is there's something wrong with the printer. Okay, but anyway, let's take a look at today's first part here, which is waves. So can you just open up the concept map for waves first? Now, wave is a very easy topic because wave ultimately just revolve around one formula, which is V equals to F lambda. Any kind of quantity that basically is a wave will obey what we call the wave law. And the wave equation or the wave law is known as V equals to F lambda that I've stated here, whereby V is the speed of the wave, F is the frequency, and lambda is the wavelength. Now, I need you guys to take note that when we talk about the speed of the wave, this is literally the speed of the wave propagating, different from the speed of the particle moving up and down. You understand? Okay, so wave is a very abstract concept in the sense that your wave is not really moving. It's your energy that is moving. The wave seems like it's moving only because your particle is moving up, down, or left and right. And because of that, you will have your particle actually having its own kinetic energy and hence its own speed. However, when we do V equals to F lambda, we are not looking at the speed of the particle, we are looking at the speed of the wave. Clear? Why do I say that? Because there is one question that actually asks the student to calculate the speed of the particle. Now, how do they do that? You use the amplitude divided by the time taken for the particle to reach that amplitude or the displacement. That would calculate the speed of the particle. Do you understand? Okay, to calculate the speed of the wave is still V equals to F lambda. Now, F is frequency, is the time taken for one wave, so F is equals to 1 over period. This one I think most of you guys should know, correct? Okay, so what kind of wave then obey the wave equation? What we call progressive wave. So inside your wave topic and in Sec 4, you learned progressive waves. And what are progressive waves? They are essentially waves that result in the net transfer of energy from one point to another. So I repeat, your waves don't move, they transfer energy. It is the energy that moves from one point to another. Essentially, it's the conversion from kinetic to potential that eventually brings from one point to another. Clear? There are two types of progressive wave that you need to know: transverse wave and longitudinal waves. What are the differences? Transverse waves are waves whereby the particles oscillate perpendicular to your wave motion. I repeat, it's the particle that oscillates, not the wave oscillates to the wave. Clear? Whereas longitudinal waves is where your particle oscillates parallel to the direction of the wave motion. So these are what you have learned before in Sec 4. Now, what is the new thing? The new thing is for transverse wave. Only transverse wave can be polarized. Important. Why? Because in the exam, they ask you, explain why only transverse wave can be polarized. So first things first, what is the concept of polarization? Now, polarization is where you rotate your light or your wave into a certain angle. Understand? Now, what for do we do that? I know the application is not that obvious to you guys, but I think you guys have tried 3D movies before. Okay, so polarization is coming into play in 3D movie because one of the lens is actually polarized parallel in this direction. The other lens is polarized in this direction. So when they merge together, one eye will see image in this direction, one eye will see image in this direction. So when they come together, that's where you see the three-dimensional image. That's how your 3D lenses are being made. Understand? In case you all don't know why is polarization important in your life. Clear? Okay, so this is how polarization is. Now, next thing, if you actually do chemistry, again, most of you guys do chemistry. Anyone here don't do chemistry? Okay, but even if let's say you don't, at least you guys have eaten medicines before, right? So medicines contains what we call isomers, and isomers are the ones that cause polarization. Okay, so usually what in physics they will just put a polarizer or analyzer. In chemistry, the polarizers and analyzers are the one that contains the isomers. Okay, so that's how polarization comes into play. So why do we need to rotate plane polarized light? Not why, but what is polarization? Polarization is the phenomena where the oscillation of your transverse wave is restricted to a single plane. Meaning to say, your light comes out as a beam and light travels in all directions. Now, to make sure that my light travels in only one specific direction, as well as an angle, I would first need to pass my unpolarized light through a polarizer. Only then, light that is in this direction will come out. Any light that is in other direction as the polarizer will be blocked by the polarizer. So end up, only light that comes out here will be polarized. Understand? Okay. Then once I want to rotate this polarized light, I will actually rotate it to a specific angle like that. Clear? So take note, only transverse wave can be polarized. Longitudinal waves cannot be polarized. Do you understand? Okay, now the next question would then be, how do we then calculate the angle at which my transverse wave is being polarized? That's where we learn the Malus law. Okay, I think most of you guys have heard of this law before. If you have not, now is the time to actually understand what this law is talking about. Basically, light is a wave. Waves has amplitude. Amplitude brings about intensity, which means any waves will have intensity. So your light will have intensity. Now, when the intensity of a plane polarized light comes out from a polarizer, according to the Malus law, the intensity of the wave will become the initial intensity multiplied by cosine square theta. Do you need to know the derivation of it? No. You just need to know that the new intensity of the polarized light will now become the initial intensity cosine square theta, according to Malus law. Understand? Okay. So I naught here is the intensity of your unpolarized light. I here is the intensity of your new light. Now, when will I have maximum intensity? If you look at the math equation, cosine theta is maximum when theta is equals to 0. So maximum intensity happens when your polarizing axis is parallel to the incident light. But cosine theta is minimum when you have 90 degrees. So when your polarizing axis is perpendicular, you end up not having maximum intensity. Okay?
Why can't longitudinal waves be polarized?
Because longitudinal wave will have a chance where it will be perpendicular to your polarizer. As a result, all your longitudinal wave will be blocked by a polarizer. So end up, you will not have any light coming out. But transverse wave will always be up, down, moving up and down. So whatever angle it is, it will always be moving up and down, not left and right.
But can we just tilt the polarizer such that all the light passes through?
So then it won't apply for all longitudinal waves already. You need to tilt the polarizer. You understand? Okay. So only transverse wave will be polarized. Huh? Clear? Okay, next thing, EM spectrum. A lot of you guys probably will skip this because it's not so important and you guys have already learned this before in Sec 4. Now, what you need to know of EM spectrum, number one, is obviously the spectrum. So if you haven't memorized the spectrum, memorize it, come up with acronym. For me, was Gorilla X usually vomits in my room. It's all the definition for that. That's how I remember. Understand? But what is more important, I realized, is actually the wavelength. I need you guys to memorize the wavelength of each of the spectrum because there is one question that we have seen that was tested on the wavelength, and they ask you to suggest a suitable EM spectrum based on the wavelength. Understand? Okay. So if you guys haven't already remember, Let me just, oh yeah, I was looking at it. Ignore the Millie Bobby Brown. I'm watching Stranger Things right now and I understood the hype as of now, why everyone is crazy about Stranger Things. And she's very pretty, I feel. Okay, anyways, here, wavelength. Can you all at the bottom copy down the wavelength? Because you need to remember at least what wavelength belongs to what spectrum. They will actually test you. They will literally give you the wavelength and say suggest a EM spectrum suitable for it. Understand? So just write down very quickly. Okay, Ken? Okay. Done?
If you go back to the part about I equals to IO cosine squared theta, this formula only applies if the light that's passed through is already polarized, right?
Yes. Not unpolarized light.
So if it's unpolarized, no matter what direction you shine at, it's always half of the original.
Correct. Okay, now let's move on to the next part here. So longitudinal waves, I don't have to go through, it's very straightforward. Basically, it's formed when you have a vibration. Medium usually sound waves. So in this case here, the medium will be air particle, creating series of compression and rarefaction. So it's a difference in pressure that resulted in your waves, sound wave being formed. Understand? For those who don't know, how is sound? How do you hear sound? For example, I'm the source, I'm speaking. When I produce energy from my mouth, that energy was used to compress the air in between me and you. Okay, so it compresses, releases, until it reaches your ear. Your ear has a drum. That compression and releases basically hits the drum in your ear. Then your brain connected to your eardrum converts it into electrical signal. That's where you interpret the signal as sound. Understand? Okay. Okay, so let's take a look at the next part here. Both under wave, you need to learn how to analyze graph. Your graph, there's two types. According displacement versus displacement, or displacement versus time. If let's say your axis is time, take note, the time taken for one wave, that will give you the period. But if your axis were to be distance, the length taken for one wave would be your wavelength. So from these two graphs, we can then calculate this thing called phase difference. Now, a lot of students do not know what phase difference is. Phase difference is defined as the difference in the oscillation path of the particle at any one point in time. Meaning to say, this particle versus the other particle, what is their phase, like how far away are they from each other? And phase difference can be calculated by two ways. Either I take the time interval between the two particles divided by the period of the wave times 2 pi, or I take the distance interval between the two particles divided by the wavelength times 2 pi. That's how we calculate phase difference. Understand? So what does phase difference mean? If let's say I have two waves in phase, that means the two waves are literally moving together in sync. You can see it like in sync. Usually, if let's say I'm in phase, my phase difference would either be 0 or 2 pi. But if let's say I'm out of phase, okay, that means when one particle is moving up, the other particle is moving down, completely not in sync. And usually this would be pi radian. Okay, so for two particles that are not in phase, the angle difference between them is pi radian. Clear? Okay, now the next thing we want to take a look at would therefore in wave would be this formula here, which is your intensity of wave formula. So this is a new thing that you don't learn in set 4. To calculate intensity, which we then can throw it into Malus law, is that the intensity of the wave is given as the power per unit surface area. Why? Because wave is radial, meaning to say that it goes in all directions. So when we look at the area that is covered by a wave, it is usually a circular area. So therefore, intensity of the wave is calculated by power over the surface area, 4 pi r squared. Which means to say, your intensity of a wave follows the inverse square law function with respect to the radius. The larger your radius from the epicenter, the lower your intensity. Why is this important? Because in superposition, you will realize the further away my waves go, the lower my intensity. You understand? Okay. And don't forget, intensity is always directly proportional to square the amplitude. I repeat, intensity is always directly proportional to square the amplitude. Not square the energy, not square anything else, but square the amplitude. Okay?
This 4 pi r squared only applies for some cases, right?
Most cases, in your syllabus cases.
In which cases does it apply? Because I remember there's another formula for a different case. I think.
J2, but not now. Yeah.
Studied it different.
JC2, you will have another intensity formula, but that one will be under quantum.
So this one is only for
Waves.
This one is for 2D or 3D?
2D.
2D.
Yeah.
Is that a 3D formula? I remember there being a 3D formula.
But won't be tested. As in, not under your syllabus. So for now, they only take all your intensity as two-dimensional radial. Understand? Okay. There will be another intensity formula, but that one will fall under quantum. That one you do it when you're in J2, not now.
Okay, so the R is just an amplitude, right?
No, it's the radius from. So your wave is like that. What? This is the source, correct? Your wave goes up like that, goes out like that, goes out like that, correct? So the radius is like that. The distance from here to a point from there. Understand? Okay, see out these as wave fronts. So the wave traveling from this direction to this direction, this one here would be your R. Okay, not the amplitude. Okay, so that will be the intensity for the waves. Any question? No, Okay, now that would be for wave. Let's take a look at superposition or stationary wave. So superposition is actually a concept. Superposition is I would like to see as a principle, a concept. It's not really a phenomenon. Superposition can be applied in 3 different scenarios. The 3 different scenarios are: number 1, standing waves; number 2, constructive interference, destructive interference; and lastly, diffraction. Okay. Now, what is superposition? Superposition is actually the principle whereby if, let's say, I have 2 waves, all right, meeting with each other, and these 2 waves are the same type, the resultant of the 2 waves will be the vector sum of the 2 waves added up together. Simply put, what do I mean? When we talk about superposition, let's say I have a wave here and the amplitude of the wave is A. I have another wave that comes in and the amplitude is also A. The resultant amplitude for these 2 waves, if I were to merge them together and they are in phase of each other, will either be 2A, or if let's say I have one wave amplitude A meeting another wave that is amplitude A as well, but in the opposite direction, 0. That is what superposition means. Understand? At every point in time, the displacement, the resultant displacement of your superposed wave will be the vectorial sum of each of the individual waves added up together. Okay? The condition, however, is that your 2 or more waves need to be of the same kind. You cannot have one electric wave and then maybe the other one is like a magnetic wave or something like that. They need to be of the same kind. Clear? Then the resultant displacement at any point at any instant will be the vector sum of the individual displacement at that point in time. Okay? So this concept is then applied to the very first one called stationary wave or standing wave. Now, what is stationary wave or standing wave? Stationary waves or standing waves is essentially a wave that is sort of like a freeze form. Now, a very good example I can show you guys is this one here.
Sink, if you like, and
So, can y'all see, right, that
constructively
at any point in time, the wave looks as if like it's freeze there, not moving, different from progressive wave. Because imagine progressive wave, your Kallang wave, your wave is moving, right? Although it's not moving, but it looks like it's moving. Stationary wave literally
interferes
freezes
with the
there,
next
doesn't
wave that
move.
comes down right at this point.
But for stationary wave, there
Now,
are
the
a few
waves
key
that
things you can
reflect,
see. You can see that there are
that come
regions
down and
where the
reflect,
particles don't move at
destructively
all.
interfere with
For
the
example, you see
incoming
when you
waves
touch,
right
it doesn't
here.
affect the wave.
And that's
Why?
called a node.
Because that particle
I
doesn't
can
move.
touch it and it still is
You
working.
understand? So that's how unique
So,
stationary
the
wave
node is not
as
moving.
compared to progressive wave. Your transverse wave, your longitudinal waves, any point you touch for the wave, it will affect your wave movement because all the particles are moving. Understand? Okay. So for stationary waves, in order for you to have a stationary or standing wave,
video, the explanation
you will need, number one, your incident wave. So an incident wave is basically a wave that you provide the source as, so an incident wave comes. Then when the incident wave reaches a point, let's say a reflector, the reflector will cause the incident wave to reflect a wave in the opposite direction. Now, it is the superposition of the incident wave and the reflected wave that results in a stationary wave. You understand? So I repeat, it is the reflection, superposition of your incident wave and its reflected wave that results in a stationary wave. You cannot form a stationary wave from one wave by itself. Clear? That's why every time you have a stationary wave scenario, there will always be either someone or something at the end to reflect it. Okay? If there is nothing, there is actually something called air particles. Clear? So for stationary wave, a few other identities, a few other things that you can see to spot there is a stationary wave is it will form a series of what we call nodes as well as antinodes. So what are nodes? Nodes are, like in the video, the regions where that guy pressed that the particles do not move at all. Antinodes are the regions where the particles move at maximum amplitude. Understand? That's one identification of stationary wave. Number two, stationary wave for one loop here, all the particles here are in phase with each other, meaning they are in sync with each other. But these loops particles are out of sync with these loops particle. Okay? So I repeat, for stationary wave, all the particles inside this one loop, they are all in phase with each other. But the particles here and the particles in the next loop are out of phase from each other. Different from progressive wave, all the particles are out of phase with each other. Okay? So that's one thing about stationary wave. Second, stationary wave, the distance from one node to one node, this will give you half a wavelength. So to find one wavelength is from one node to the third node. Understand? Okay, so this is what we call stationary wave. So like they will test you, how is stationary wave being formed? When you have two similar waves, now you know the similar wave is the incident wave and the reflected wave with same speed, same frequency, same amplitude, traveling towards each other in opposite directions superposed.
Does it need to be the same amplitude?
Best to have the same amplitude if you want to have an observable stationary wave. Otherwise, right, you will see a stationary wave with like, I don't know how to explain, but in the video, it's like wobbly wave. It's not very distinct curve, zero curve, like curve like that. Okay, so best to have same amplitude.
Then when we consider a stationary wave, do we think of it as a different concept compared to transverse waves?
Yes. It's completely two
But it's
different things.
based on transverse waves, right?
No, it looks like a transverse wave because of the curve, but it's not a transverse wave because transverse wave, the particles transfer the energy from one point to another. But stationary wave, the energy is not transferred. It's stuck within that position. So if I here, I put a difference. If you take a look at energy, stationary wave, there is no translation of energy. Your energy is retained within the vibration of the wave. But transverse wave, which is your progressive wave, energy is transported in the direction of wave propagation. So yes, it is based off transverse wave because of the up-down of what do you call it? Oscillation, but it is not transverse wave.
So it's from using transverse wave. Then do we apply the same formulas from transverse waves for stationary waves?
V equals to F lambda?
Yeah,
Yes, because they are still waves. Okay, can? Okay, but the most important thing for standing waves, other than how the standing wave being formed, would be this one here. I'm not sure if any of you guys understood this concept, the open close ends, close ends, and the double open end. But for all of these scenarios, you need to know how to derive the fundamental frequency at least, and the next few frequencies. Okay, so summarize this part here. How I do it is this, okay? Don't memorize, just deduce. Let's say if I have, for standing wave experiment, number one, I have two ends closed. How do I deduce a standing wave from this? Two ends closed means I have literally just have a box, correct? Now, all standing wave will have nodes and antinodes. All nodes will form at the closed end. So for two end closed end, I will have two nodes by the side. And then this is how my standing wave would look like. I have a node here, I have a node here. And this is what we call the fundamental mode. One standing waveform, one stationary waveform. Okay. At this frequency, the fundamental frequency, how do I know what frequency is this? First things first, the length of the spring is given as what? This entire thing here, right? So this is the length of the spring. And the length of the spring, based on the definition of stationary wave, is equals to half the wavelength. Do you agree? From one node to one node. Which means the wavelength of the stationary wave is given to be 2L. So to deduce the fundamental frequency of this particular stationary wave, we will take the speed of the wave over lambda, which gives me V over 2L. So for any scenario, two ends closed, my fundamental frequency is given as this formula. Understand? So now, when is the next frequency I will see another stationary wave? So I'm going to up my frequency vibrator, up it. When is the next time I'm going to see a very nice stationary wave? That is when I have the same box, but instead of one loop, I will now form 1, 2. As long as I make sure my both ends is nodes. Can you see that? So same thing, this is what we call the next harmonic mode. Now, what harmonic mode am I looking at? I'm not sure yet, so let's deduce. Okay, I put here harmonic mode first. Now, same thing, the length of the spring is given as L. And for this mode here, L is the same thing as lambda, right? Which means to find my frequency for this mode here, V over lambda, which is V over L. Now, how is V over L differentiated from your fundamental frequency? You realize it is 2 times of your fundamental frequency. So that means, let's say, if at 1000 hertz, I saw a stationary wave, the next time I'll see a stationary wave will only be at 2000 hertz. Do you understand? The next round I see a stationary wave will be at 3000 hertz, 4000 hertz. So this is what we call the second harmonic motion or second harmonic mode. Yeah? Don't memorize, derive. Okay? So you need to know the one for 2 ends closed and 2 ends open. So what happens if I have 2 ends open as well? Same thing. Do not memorize, derive. First things first, fundamental mode. So I'll have 2 ends open. Now for open ends, what is formed at the end? Node or antinode? Antinode. So in order for me to have an antinode here and an antinode here, and fundamental stationary, my graph would look, my wave would look like that. Open, open, with a node in between. Am I right? So same thing, let's deduce the fundamental frequency. This is the length of my string. So what's the fundamental mode? The fundamental mode is equivalent to My length of the string is how many of my wavelength? How many of my wavelength give me the length of the string? Half. You see? 1/4, add up together, half. So half a wavelength. So the wavelength is equals to 2 times of L. So what's my frequency? My fundamental frequency, V over lambda, which is V over 2L. Okay? So then let's move on to the next frequency. The next frequency, I don't know what mode is it. Let's deduce. So first things first, I need to have 2 open ends. 2 open ends means 2 antinodes. But how am I going to draw this? Node, antinodes at the end, node, antinode. Antinode, node, antinode, like that. So antinodes, node, antinodes, node, antinode. Okay? So now, this is the length of the spring. What is the length of the spring equivalent to? How many wavelength? Three-quarter. Three-quarter or 1 wavelength? 1, correct. Cause 1/2. Understand? So the length of the string is equals to 1 wavelength. So the next frequency will be V over lambda, which is V over L. And just nice, 2 times of my fundamental frequency. So we call this second harmonic mode. Understand? Which is the same concept. The first time, if let's say I were to see a stationary wave, is at 1000 Hertz. The second time I see a stationary wave would be at 2000 Hertz. You understand? Okay. Then comes the tricky part. What happens if I have one end open, one end closed? So one end open, one end closed. Now, for one end open, one end closed scenario, I will have, let's say, like an air column like that, correct? It's too big. So at the closed end, I will always form a node, open end. So antinode, so you will have like that, and then you will have like that, correct? So fundamental mode. How do we get the fundamental mode? First things first, what is the length of the spring equivalent to? 1/4 of the wavelength. So length of the spring, 1/4 wavelength. So wavelength is 4 lambda, correct? So to calculate the fundamental frequency, V over lambda, which is V over 4L. Okay, so this is my fundamental mode. Now, the next one, harmonic mode. When is the next harmonic mode, or how do I find the next harmonic mode? Same thing. I'm just going to extend this thing to form a open, close, by the way, I'm very bad at art, just saying. I failed my art when I was in lower sec. Who fears art, right? I know. Me. Okay. Yeah, like that. Can you see what I'm drawing? Can Okay, so this is the next fundamental mode, the next harmonic mode, whereby you have a node here and you have an antinode here. But if you were to deduce, what does the length of the spring equivalent to? 3/4 of your wavelength. So that means your wavelength is 4/3 length of the spring. To calculate the next frequency, V over lambda, which is V over 4/3L. Now, basic math, this would be 3/4 of my L. All right? V over L, I mean. Now, how does this compare with my first fundamental mode? Do you all realize? 3 times of my first fundamental mode. So instead of second harmonic mode, this is my third harmonic mode, which means to say, for one end open, one end closed. If I saw a stationary wave at 1000 hertz, then the next time I see a stationary wave would be at 3000 hertz. And the next time, 5000 hertz, 7000 hertz. So both end open, both end closed. The stationary waves differ each other by integer multiples of the frequency. But if one end open, one end closed, the stationary wave differ by odd integer multiples of the frequency. Understand? Okay. So please remember, do not memorize, deduce it so that it's easier for you, so you don't have to memorize so many things. Can? Okay. So that is one very important aspect of stationary waves. Any question? No. So once you are done, question time. Can you take out the question that I given you guys? Okay, now let's take a look at this question first. I give you guys a while to try the questions before I go through. Okay, yeah. This one here, question 3. It's a stationary wave question, quite obvious. Closed end, open end. Okay, hopefully you guys can see the question. I'm gonna just flash it here. Now I give you guys about 5 minutes. Maybe you guys can try this question. Okay, now let's go through this question. Hopefully it wasn't that hard because it just requires you to draw the waveform. Now, it first says here, a long tube filled with a tap is filled with water. A tuning fork is sounded above the tube as the water is allowed to run out of the tube as shown. So the first time they heard or they saw a stationary wave is at figure 6.1 here. A loud sound is first heard. So this is when you have your stationary wave observed here and at the maximum amplitude. Then when the water level is as shown, and then again, when the water level is shown next at 6.2. So if this is the fundamental mode, this will be the next mode. One end open, one end closed, correct? They said on the figure, sketch the form of the stationary wave that is being set up. So how do we do that? At the closed end, we're going to draw a node. At the open end, we're going to draw an anti-node. But make sure this is the next fundamental frequency. So open, closed, and then. Yeah, I know. Give me a while. Open. Make sense? Okay, artistic enough. Okay, but make sure that the other part is is dotted line to show the other fundamental frequency. Clear? And you have a node here and you have an anti-node here. Now, the next question, they say, mark with letter N the positions of any nodes. So I don't draw my anti-node because they did not ask me to do that. I'll just write my nodes and my nodes here. Hopefully you all got it. Yes, huh? Okay, now, then the next thing, it says, the frequency of the fork is 512 Hertz, and the difference in height of the water level between the two positions is given to be 32.4. Calculate the speed of the wave, sound wave. So to calculate speed, we know what formula do we use? V equals to F lambda. Now the question has already given me the frequency, my F. All I need will be my wavelength. How do I find my wavelength? They say the difference in the distance between these two is 32.4. So what is the difference between them? This is how many of a wavelength? 1/4 of a wavelength. This is how much of a wavelength? 3/4 of a wavelength. 3/4 minus 1/4 will give you half a wavelength, which means half a wavelength is actually equivalent to 32.4 cm. So to find one wavelength, 32.4 times 2. So this is 64.8 centimeter. Understand? Then from there, V equals to F lambda. My frequency is 512. What's my wavelength?
400 times 10 to the power negative 2.
Yes, don't forget to change it into meters. You understand? Okay, or in SI unit. So in this case here, you have 0.648 meters. So therefore, you should get 332 meters per second. Now, another way to find out if your answer is correct is because this is speed of sound. You remember speed of sound in air is around 330 meters per second. So that's how you check as well. Okay, clear?
How do you know this part is a 104 wavelength? How do you know this part is 104 wavelength?
Because it's a node and an anti-node. Between two nodes is half a wavelength.
So when school taught me there's such a thing called end correction.
Yes. End correction is basically a little part that comes out from your column. So usually if let's say it's given in the question, you minus away the end correction from your length of the tube. But end correction, usually they won't count for A levels. Yeah, some schools they teach them.
Explain a bit more about end correction.
Okay, so in my wave, stationary wave here, right?
Yeah.
Now, when I especially have one end that is open, okay, I will have this little thing that comes out called end correction. Maybe I show you guys this one is easier to see. Give me a while. Superposition. Okay. These are curated notes, by the way. We don't have it. But okay, basically, right, for end correction, right, what they are trying to say is this one here. If let's say, right, I have an antinode at the surface, correct? What happens is that my wave, right, will actually come out a little bit away from the tube. So by right, we took the entire length to be from here to here, the length of your string or your length of the wave that causes the stationary wave. But because of end correction, our actual length is increased by a little bit. So you want to find a more accurate value, you should take your length minus away the end correction. Then that value you say equals to 1/4 wavelength. That's all.
Do we need to know why this occurs?
No need. Okay, just know that there's a little displacement that comes out.
So this means that when we are given something like this, we can't straight away. So let's say we're given the distance of this. We cannot straight away calculate the speed using this.
Have to, because end corrections A level usually won't test you on. So you just take that length as per normal. Don't have to minus away anything. Unless they specifically tell you, I have an end correction of this. Then you have to minus away. Understand? If they didn't say by default, just take there is no end correction. Yeah? Okay? Okay, now let's take a look at this part here now. The next question I want to ask you guys is, however, though, there's an incident wave that came from the tuning fork, right? All right. Then how is the reflective wave being formed? By reflection from the water surface. Okay? Okay. Okay, now the next part. The length of the air column is taken to be what? 15.7 cm. Suggest where the antinode of the stationary wave will most likely be found. Antinode of the stationary wave produced. They already tell you the length of column of air is 15.7. So if you go up to the diagram for 6.1, they are saying that the distance from here to here equals to 15.7 centimeter. All right? Okay, so the question here is, suggest where the antinode of the stationary wave that is produced in the tube is likely to be found. Y times 2. The distance between what? The distance between two antinodes is half a wavelength. Okay. I have a node here and I have an antinode here, right? That means 1/4 of the wavelength is equals to 15.7 cm, correct? When is the next time you actually find an antinode? If we do this, we do this, correct? Correct? So this is the next time that you will find an antinode up here. Am I right? So one wavelength will be equals to 15.7 times 4, right? Now what's 15.7 times 4? 62.8. However, the next frequency where the next time where I find an antinode will be how many of a wavelength? 3/4. 3/4 of a wavelength, because you have half a wavelength here and 1/4 of a wavelength, correct? So what's 3/4 of the wavelength?
Because the wavelength doesn't change, right? We found wavelength in the previous part, right?
68 point, wait, give me a while, 68 point. $15.7 times 4, 62.8. Okay, I get the question. Now, end correction plays a part in this question here, part 3. Okay, now what is going on here? First things first, we found the frequency of we found the wavelength of the wave earlier on to be 64.8, correct? That is the wavelength of the sound without any, that means based on the frequency as well as based on the distance difference that they gave us. Now, if let's say they said here that the length of the column of air in the tube here is 15.7 cm, that means from here to here, ignore this one here, the length of the tube here is given to be 15.7 cm. Now, earlier on, our frequency was given, our wavelength was given as what? 64.8 centimeter. If we were to do a comparison of 1/4 of a wavelength, 64.8 divided by 4 would be 16.2 centimeter. So by right, my antinode should be 16.2 centimeter above my water surface. Or you can say 16.2 minus 15.7, the difference above the top of the tube. You all get what I'm saying? Okay, I repeat. Based on the calculation earlier on that we based on frequency of the fog, as well as based on the height difference, the wavelength that we calculated was 64.8. However, when we were to look at, actually, when we did calculate the length of the tube, it was 1/4 of a wavelength, 15.7 cm. By right, if we were to use the calculated wavelength to calculate 1/4, I should get an actual value of 16.2 cm because of end correction. Understand? This is theoretically based on just frequency and difference in length calculated without any end correction. Clear? So in this case here, your antinode will either be two ways you can write it. You can say antinode is 16.2 centimeter above water surface. Or you can say antinode is 16.2 centimeter minus 15.7, which is 0.5 centimeter above the top of the tube. Understand? And that's where you will see your antinode being formed. Clear?
This is an example of end correction, right?
Yeah.
So essentially they will test it they will test it, but they won't tell us that
There is end correction, correct? Because by right, end correction is not really say under your syllabus. They won't literally use the word end correction in the exam. I've never seen the question as of now, especially for A level, but they will still test you the concept of end correction, like this kind of. Okay, but then again, this is a prelim question, so it's not really an A level question. So your school might test you if they teach it to you. So you just take note of that. Okay. Any of your school, everyone's school's done superposition already? All the end correction?
Not tested.
Not tested.
Yeah.
All the end correction? Yeah, so some schools test, some schools don't test, some schools teach, some schools don't teach. So if your school teach, might come out for your exam, so just take note of it. Understand? But A level, they rarely come out and corrections. Okay? Okay. Okay, now let's take a look at the next question. Can you guys take a look at this part here? Not this one. This one is a repetitive question. This one here, page 85. There is a uniform string causing a stationary wave being formed. This question is more technical. You need to calculate all the different values. Okay, can you guys give this question a try? Can see or not? It's a bit blur. It's 1/8 now, by the way, this one. You guys cannot see. It's 1/8L, 1/8L. Yeah, do you know where the washroom is? Oh, it's beside the leaf. Just like. Okay, now let's go through this question. Hopefully it's very straightforward. It should be a quite easy question for this in this case. It says a uniform string is held between a fixed point P and a variable frequency oscillator as shown. So your oscillator causes the particles here to actually oscillate, and then it hits a reflector, and then after that the reflected wave comes out, superposed to each other, hence forming a stationary wave. Understand? Now remember, this is basically a node here and a node here and a node here. That means you have two loops of particles, one here and one here. Okay? They say the frequency of the oscillator is adjusted so the stationary wave is shown. Point P and X are 2 points on the string. X is a distance 1/8 length from the end of the string, and it vibrates with frequency F, amplitude A. Y, on the other hand, is a distance 1/8 length as well from end P. What is the frequency of Y? If this one here, amplitude A, frequency F, can somebody tell me what's the frequency for this? F, why F?
Because they allow us.
And the frequency of the wave came from who? Oscillator. Your oscillator don't change, your frequency can't change. You understand? Okay, so the frequency here would just be F. What about the amplitude? Now, at 1/8 distance from a side here, the amplitude from the equilibrium is given to be from here to here for point X. Similarly, at 1/8 length from point P, the amplitude is given to be here. Can you see it's the same amplitude, just in opposite direction? So therefore, the amplitude here would be A. Okay? However, what is the phase difference between the 2 points, X and Y? Are they in phase? No, but are they out of phase? Yes, remember, for stationary wave, the particles in one loop in phase with each other, but they are out of phase with the one in the other loop. So in this case here, you will have pi radian. Okay, if you want to do degree, you can do 180 degree as well. All right, now the next one. It says, state in terms of F and L, the speed of the wave. How do we calculate the speed of the wave on the string? V is equals to F lambda, correct. So in this case here, V is equals to F lambda. I have my frequency F, but what about my L? How do we find L here? Anyone? What's L? L is equivalent to?
Lambda.
Yes, lambda. So in this case here, you will just have V equals to FL. Okay? Okay. Now, the next one. The wave on the string is a stationary wave. By reference to the formation of a stationary wave, explain what is meant by the speed stated in part 1. What does this mean here? Now, when we do V equals to F lambda, we stated that that is the speed of the wave propagation. But now this is a stationary wave. The wave is not moving. So what speed are we actually calculating? That's what they're trying to ask you. Okay? So if you understood the concept of stationary wave, your wave needs to travel at least to hit a reflector, then travel back. So the speed that they're talking about is the speed that this wave is traveling to the reflecting end, and also the speed of the reflected wave. Understand? Okay, so in this case here, we say the wave is reflected at NP where both the incident and reflected wave interfere as they are traveling in opposite direction. So the speed calculated is the speed of the incident or reflected wave. Okay, 3 marks because they said by reference to the formation of stationary wave. So you kind of need to bring in the principle of stationary wave or the formation of stationary wave in. Okay?
You're saying the speed of the instant wave enough to answer the question. Or do you need to say something like, is the speed at which energy is propagated for the instant wave?
Speed of the wave is enough because that one only 1 mark. The other 2 marks is for the formation of a stationary wave. Yeah.
Okay, could you repeat why the amplitude is A instead of A?
Okay, so here, you see 1/8 distance away from the end here, the amplitude is from here to here, correct? 1/8 distance from end here, can you see the amplitude is the same? So that means, right, for the maximum amplitude happens at half the length. Maximum amplitude happens at half the length. So it's actually proportional. Meaning to say that if let's say I'm 1/8 distance away from here, my height, my amplitude is this. 1/8 distance, my amplitude would be the same. Meaning, right, your wave is symmetrical like that. Correct? Same amplitude for each of the particle at same positions. Not same position, but same position from the end. Clear? Okay, any question for this one? No? Now, can we move on to the next part, which is the next principle that makes use of superposition, which is called interference. Now, interference is actually one of the more interesting applications of superposition because interference is the one that gives you a pattern to see where you can see a series of what we call bright and dark fringes. Okay. However, a lot of students tend to mix up the conditions needed for interference. So we take a look at what interference is first. When we talk about the concept, or rather the application of interference, we are saying that 2 waves are superposing to each other. 2 or more, but for our syllabus wise, we usually deal with 2. That means you have 2 sources. 2 sources producing 2 waves that will superpose together to give a resultant wave whereby the displacement is the addition, vectorial sum of all the individual waves add up together. That's interference. However, in order for you to undergo interference, the conditions is you need the same kind of wave and they must overlap each other. Okay, so this is pretty standard. The more important one is how am I able to see a very nice interference pattern? Meaning you can see a very distinct bright fringe, dark fringe, bright fringe, dark fringe. And the conditions are as such. Number 1, you will need your 2 waves to be coherent. Now, what does coherent means? Means the 2 waves maintain at the same phase difference. Doesn't mean that they have to be in phase with each other or they have to be out of phase from each other. Understand? It just means that if they were initially out of phase, they keep maintaining out of phase throughout the entire interference pattern. Clear? So they must be coherent. That means having a constant phase difference. The second condition is they must have roughly the same amplitude. And lastly, they must either be unpolarized together or polarized in the same plane together. Okay? Yeah.
Why do they need to be roughly the same amplitude?
So that your bright and your dark is distinctive. Because if let's say you have AA, your bright will be 2A. But if you have AA, your dark will be 0A. So then you can see a contrast between the dark and bright. If you have 1, 2A, 1A, right, then end up you will have bright being bright, but your dark being not so bright. Then when you put them together in a pattern, it's very ambiguous. You can't see where the bright and the dark fringes are. Okay?
Then is the requirement of coherence and either unpolarized or polarized the same thing? Something that's required only for observable interference?
Yes.
Or is it for superposition in general?
For observable interference pattern.
So without these 2, there will still be superposition?
Yes.
Just not
observable interference. Correct. That means you can't really see a pattern.
Can you explain the third point?
Unpolarized.
Yes.
That means either your light is both of them like that, or both of them like that. You can't have one unpolarized and one polarized. Like that, end up, right, you will have a spectrum that is not bright, not dark. You can't see any difference at all. Understand? Okay. Okay, so those are the conditions for observable stationary waves. Now, the next thing is, what are all these bright and dark fringes, loud sound or soft sounds that you will see inside your application? Is the phenomena of forming what we call constructive interference and destructive interference. Okay, constructive interference is formed when your two waves meet in phase. I repeat, constructive interference is where your two waves meet in phase. It can be your two waves at the start anti-phase with each other, doesn't matter. But the moment at that particular point they meet in phase with each other, you will have constructive interference. And then you will have maximum amplitude, maximum intensity, because intensity is amplitude squared. But destructive interference is where your two waves meet out of phase. So your two waves can start off being in phase with each other. But the moment they meet at that point, one goes up, one goes down, then you will have a destructive interference. Do you understand? Yeah.
How can two waves start in phase but meet in anti-phase?
The path difference they travel is different. Do you understand? Okay. So when they meet in anti-phase, you will have minimum resultant amplitude, minimum intensity. You realize they use the word minimum and not zero, because zero only works if your amplitude is exactly the same for both waves. Okay. Sometimes you might not have a question that have both waves having the same amplitude. So you use the word minimum intensity. Okay, it's not a dark patch, but like a dimmer patch that you see. Clear? So how do I know for two sources, I will meet in phase or meet out of phase? That means will I form constructive or destructive? That's where I look at the conditions. But before you look at the condition, take note. You must always check whether your sources are in phase with each other or out of phase. If your two source or your waveform comes out are in phase with each other, and if the path difference calculated was integer multiple of your wavelength, then I will have constructive interference. Meaning to say, anybody don't understand path difference? It's the distance traveled by the wave. So let's say this is my source. The distance traveled from my source to a point that I want to look at, that's my path of A. Then this is my source for B. The distance that my source travels towards the point that I want to look at, this is my path for B. So path difference means I will take the path of A minus the path of B, modulus, depending on who is the larger one. And if let's say this path difference is integer multiple of my wavelength, like 1 times, 2 times, 3 times, 4 times, I will get constructive interference. If the path difference calculated, can you cancel away the odd, is integer multiple of half a wavelength, then I will get a destructive interference. You understand? Yeah.
I was wondering if path difference and phase difference are two completely
Different thing.
different things. They're
Yes.
not affecting each other.
No. Okay. So that is if your particles are in phase, your sources are in phase. Now, take note, I've written here. If your sources from the very start are out of phase from each other, then the conditions swap. Meaning, for constructive interference, it would be integer multiple of half the wavelength. Destructive interference would be integer multiples of the wavelength. You understand? So at the very start, always check, is it in phase or out of phase first? The question will state. If the question don't state, then they will say coming from the same light source, then that will mean in phase. Okay, understand? Okay, so that will then form the series of constructive interference and destructive interference. Any question? No? Okay, good. So, wait, let me just take a look at something. So for interference, this concept, together with superposition, that concept, they put it together and then they came up with this thing called diffraction, or the phenomena of diffraction. Okay, Now, diffraction is one of the hardest one that a lot of students tend to not be able to understand because it's very hard to see. But essentially, what diffraction did was, you guys can go to YouTube. Usually I show my class the Thomas Young experiment, what he did, but it's a bit long. So you guys can go to YouTube and just search this BBC documentary about him. But anyways, what he did was he actually shined light. Never mind. Let me just show you guys then. It actually brings all the way into quantum, not so much into just waves by itself. Yeah.
The answer to that question of whether light was a particle or a wave would prove to be complicated. Now enter Thomas Young,
Just skip to the part.
the man who exposed the enigma at the design of an experiment that sent physics down the rabbit hole we still live in. It looks simple, right? How could 3 sheets of cardboard set such a catastrophe in motion? A green glass shade like this one will only allow the green light through, so that only a single color or frequency of light will pass through the slits. Why was that important? Because he assumed that the many overlapping colors would result in the same light waves that Huygens imagined, called an interference pattern. He forced that single color of light to travel through 2 separate slits to see what kind of pattern the light would make on that last piece of cardboard. If light was a particle, you'd expect to see 2 distinct clumps of light in the opposite wall, where the individual particles of light ended up after they passed through the slits. But that's not what happened. Instead, a completely unexpected pattern.
Yeah, so that was what is going on in Thomas Young's double experiment. He was the guy who sort of sealed the fate that light is a wave. Right now, we all know light is a wave because that's what we learned. But last time, they didn't know whether light was a wave or a particle, because some people believe it was a particle, some people believe it's a wave. J2, you all will learn quantum physics. That's where they will throw you this question, and you probably will have to choose side, whether light is a wave or light is a particle. Okay, then you can go and further your studies on that. But Thomas Young kind of sealed the fate that light was a wave, because if it's a particle, particles choose holes. Right? Am I right? I either go left or I either go right. That means the pattern that I see will just be a block on left or a block on right. But when they did the experiment, they realized instead of just left or right, it forms a series of patterns. Bright, dark, bright, dark, bright, dark. You see that? So his experiment basically was because of diffraction. Now, what is the concept of diffraction? It's actually what we call the redistribution of energy. Meaning to say, when my wave passed through a hole, or in physics, we call it an aperture, the wave, instead of traveling forward, they will somehow squeeze through this small little hole and redistribute the energy coming out in this manner, like that. Okay, the conditions, however, is that this hole or this aperture need to be roughly the same size as the wavelength of the wave. If this aperture became too big, your diffraction effect is much reduced. So you won't see much diffraction effect. You will just see like your wave passing through as per normal. Understand? So the condition is the whole aperture must be at least close enough to your wavelength. Okay? So diffraction essentially is the redistribution of energy through the spreading of waves into what we call geometrical shadows. Okay?
May I ask, in drawing, can we just draw the waves if the slit separation is greater than the wavelength?
You mean straight line?
Yeah.
No, just try to draw a bit of curve. Yeah. Otherwise, it just seems like your wave just teleported through the hole or something like that. Okay? Ken?
Wait, the slit opening can be smaller than the wavelength, right? Or would it be bad if it's too small also?
Nah, too small also cannot, because the wave can't pass through. So can be smaller, you will just have more pronounced diffraction pattern, like more curvy. But you can't be too small because the wave can't pass through.
Do you need to know why that happens? Why it comes?
No, but it's actually your wave redistributing its position and energy. Okay, so using that concept, that's where Young double slit came about. Now, what did Ernest Young did that. He first passed through light of a certain wavelength, monochromatic wavelength, because you want to have an observable interference pattern, you should not have a light source that have multiple wavelengths. Otherwise, you end up having one interference pattern for green, one interference pattern for red, one interference pattern for pink, then end up it's just a whole mess. Understand? So that's why he chose green. It's a single wavelength. He passes through a slit so that he makes sure that all the light that passes through is in one direction. That's him polarizing the light. Understand? So that you don't get light waves in all directions. Now, when this light comes out through the aperture, what happens? It will just redistribute like that. Then in order to create a two source so that he can do constructive or destructive, he passed through a double slit. So light comes out like that, light comes out like that. Can you see that? Then the moment the two waves meet each other, that's where superposition happens here. You understand? So the waves will overlap, hence forming a series of bright, dark, bright, dark, bright, dark. Yeah? You realize the central wave, because at this point here, will always be the central maximum. But at every integer multiple order, do you realize constructive interference is formed in phase? But at every half of the integer multiple wavelength, destructive interference is formed. Okay? So that's how he did the experiment, and that's what he see. So to relate or to come up with a formula to equate, number one, the distance between the slit and the screen, the fringe separation, the slit separation, and the wavelength together, Ernest Young came up with this formula, y equals to lambda L over D. Your school probably use some other parameters, but it's the same thing. To calculate the fringe separation, it is the wavelength of the wave times the distance between the slit and the screen over the slit wave. Okay? So this formula only applicable for double slit experiment. Yeah? In your exam, you got double slit, you know this is the formula you use. Okay? Obviously, modern science, they don't just stop at 2 slits. What do? They ask the question, what happens if I up my slit? Instead of 2, I do 10. Then became 5,000, then became 1 million, then became many slits. So that's when diffraction grating comes about. So diffraction grating is when instead of just 2 slits, I up my slit. But no matter how many times they increase the number of slits, they realize the interference pattern is the same. It's a series of bright and dark fringes. Can you see that? Okay, so the constructive interference happens when you have a series of dark bright fringes. Destructive happens when you have a series of dark fringes. Okay. Now, intensity then come into play. You all realize that at the central maxima, the intensity is the largest. But as you travel further and further away, what happens? Correct. So the intensity starts to decrease. Okay. So according to diffraction grating, with n number of slits, I can make use of my order of interference to calculate what my angle is. Meaning to say, let's say this is my first order interference, constructive interference. In layman term, my first bright fringe. What is the angle does it make with the central maxima? I calculate by using d sine theta equals to n lambda. Okay? So for this part here, d would be my slit separation. That means the separation between the slits. Sine theta, the theta here is the angle that it makes from the central maximum. N is the order number. Order number means is it the first bright fringe, second bright fringe, or the third bright fringe? And lambda is obviously the wavelength. Okay, so this essentially is what diffraction grating is about. So if your question poses diffraction grating, usually you know you use this formula. If your question poses double slit, usually this formula. Okay.
What about the sine theta and tangent theta formula for the double slit?
That one is just math. That one is to help you to derive this equation.
Will we not be using it?
Then it's the derivation of this formula. How do you derive this formula? But derivation of this formula, you don't have to. They won't test you on derivation.
So it's not likely that there'll be a question which will require you to use either of those formulas.
No. But your school might test you if they want you to know.
So can I ask why there is a difference in intensity even for double slit?
Because same thing, what? The wave is still spreading radially. That means your R is still increasing. When your R is increasing, your intensity will decrease.
Oh.
Understand? Okay. Any question for this one? Now, there is one part called Rayleigh criterion. That one I only go through in class because it's a whole new concept on resolving. I think you guys have already seen this type of question before. Like, let's say, I saw one type of question before. Like, if I'm standing up on like a certain distance away from the floor, and then there's a hair on the floor, at what angle will I be able to spot the hair? Something like that, resolving. So that one is Rayleigh criterion. I know, it was like the hair has a certain thickness. At what angle when I look down will I be able to see the hair? If it's beyond the angle, will I not see the hair? That one is called Rayleigh criterion. Okay. But this is for superposition as of now.
What about like the missing maximum?
Missing maximum?
I don't know. Wait, what's the official definition? That's what my school has it called.
Missing maximum? What about the
When
missing?
the intensity envelope reaches.
Oh, that's Rayleigh criterion.
Oh, that's part of it.
Yes, that's Rayleigh criterion. Okay, so I give you guys a short what first is this one here. Okay, so now we all know diffraction grating needs 2 slits, correct? What happens if I only have a single slit? But I want that single slit to also diffract. So when you have white light that passing with all colors that is passing through a single slit and then many different diffraction grating, I can actually make 2 double slit behave as if as a single slit. Okay, how so? Let's say I have 2 light sources very, very far away from each other. The 2, because they are very far away from your screen, it looks as if like 1. Okay, now that 1 point source happens because the 2 light source overlaps from each other. So Rayleigh criterion basically tells you what is the minimum angle that these 2 sources must be away from each other such that they look like 1. Okay, now for that to happen, the formula is theta equals to lambda over b. Okay, now for theta equals to lambda over b, the lambda here is the wavelength, the b here is basically your slit separation. And Rayleigh criterions only work if the maximum of one of your wave meet the first minimum of one of the wave. Okay, so instead of seeing 2 point source, you see 1 point source. But it came from 2 point source. Okay. Okay, clear?
But there is only one single slit. How come there are 2
Slit width.
slits?
Slit, the slit is like that. This is your B. Okay, not that you need 2 slits to form a slit width. Okay. 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 So for the next class, if you guys joining, then we'll talk more about Rayleigh criterion. But so far, this is up for superposition. Okay. I've given you guys some practice question for superposition. You can go back and try. I'll upload the answer key onto the Google Drive link that's in the Telegram. Then y'all can go and check your answer to it. Okay. Any questions, y'all can just still PM me privately on Telegram. I think my name is on the Telegram chat if I'm not wrong. Yeah? Okay. Then if you're joining for session 2, we'll go through gravitational field. Gravitational field. Yeah. Okay. Oh wait, before that, I need to go through this one very quickly. I just need you guys to fill up a Google form. Okay, so basically for joining us wise, these are the deadlines, but they will just periodically upload in the Instagram line if you need the timeline in terms of sign up for September's, October's, and November's. But today's session, can you all just fill up a Google form and just create a feedback very quickly? Okay, you can keep the concept map. Is for you guys to take home and revise.
Do I fill in again?
No need. For those, yeah. For those who join camp, no need to fill in. For those who haven't, then you can fill in. Okay. Keep the concept map. Add on to your own stuff if you need. Those online can also fill up the concept, the Google form. Yeah.
So when I clarify for diffraction grating, there is no need for polarizer, but for Young's double slit, there needs to be a polarizer.
Not necessarily the case. Diffraction grating, if you don't use a monochromatic light, then you have to have polarizer.
And most diffraction grating at single slit are one slit.
Mm.
Thanks.
Okay, any questions? Yeah.
What would be the difference between diffraction grating and a single slit? Is there any difference between diffraction grating and single slit?
In terms of what? Diffraction grating has multiple slits. Single slit is one slit. So interference pattern will be like that. If let's say you have a single slit, right? The pattern probably will look like that. Central maximum, very small energy distribution at the end. But if diffraction grating is not so immediate drop. Okay. Okay, that's all. Have fun studying.
This one won't go these days always been here or this one know that it's actually local. Why can't that be more so you use the wait, so it's based on this one. So the next one. Oh, so it's always like this.
Then the next one will put another because unless you say this is the third one, then you have to draw. Okay. No problem.